The next speaker is Razak, understanding solitonic excitations in the charge density wave ordered state of indium silicon 111.
Okay, so my name is Samana. I'm a PhD student at Max Planck Institute in Düsseldorf, so I will talk about this. Essentially, I'm extending the talk of my supervisor given early this morning, how the structural transition happened at the quantum limit in these nanowire arrays. And in the morning, he tries to establish this first link. He draws your attention that how the optical excitation can create and break the indium-indium bonds, leading to the non-thermal excitations of these soft phonon modes, and drives the structural transition in the limit of quantum critically damped nuclear motion and the accompanying of those phonon modes. That was all about. He was talking about to complete this part of the story. But the thing is, when we get the ground state, it comes out that it's the four-fold degenerate ground state, whose optical excitation can lead me for the topologically protected solitons, which follow the four-element abelian algebra. We want to use these kind of structures to carry quantum information in the form of quantum bit for quantum computation. That's the part of the story. So this abelian algebra is very important, which is coming in these three flavors, that is the right chiral, left chiral, and antichiral soliton. But the point is, these solitons move too fast to be imaged by an STM. So we want to make their atomistic model, we want to freeze them in the phase space so that we can extend their dispersion relation and all these kind of processing information. So that's my task. So essentially what I want to do is the trapping. So how this trapping can work, you can see there's some features are more brighter and then some are like dim features. So the thing is why these are bright and what does this mean? But before going to that, you can see here is some soliton is passing by. The first thing I need your attention is that these are the bright features and they are undisturbed throughout the upper chain. It's a double pile chain system. While in the lower chain, you can see the bright feature is shifted at this point and also at this point. We can calculate that this shift is about 3 lattice constant, but the point is the combination of this unbroken and broken chain can have two kinds of effects. It can be used to trap the soliton inside the wire or intra-wire coupling. So these are both left chiral solitons. One is the trap in the wire and one is the passing wire. But the thing is, this bright features and this is the dim feature. To establish the atomistic model, we can carry out the absorption energy calculation in such a way that we can search for all the absorption in the indium atom. And we find out that both, with respect to the substrate symmetry, both FCC and HCP sides are the minimum energy configuration, where the HCP side has the lowest energy configuration lies here. But their difference is really minute. The point is that we are here at this structure, and we relax the structure without any further constraint. The next thing we did, if we remove this erratum and we call it a defect without an actual defect, we can reach this point. And this is also a local energy minimum. Now I want to convince you that this is a short left chiral soliton in a fashion that how the Professor Young group published the paper in 2 papers in Nature and Science in consecutive 2 years. The point is, before going to that, I want to establish this model. We want to validate our model such that these are our structures. You can see the positions of the colored triangles here. These are the same position in my simulated and the Meyer STM images. So this is clear that this we are focusing, for example, in the field state images. This is clear that this is an additional addendum. But what about this one? as I claimed, this is a left chiral soliton, and we would like to understand its dynamics. So before going that, let me take you through a little bit of the nomenclature, and that work like this way. So we have 4 degenerate ground state, for example, and moving always in the clockwise dimension, we will get always left chiral soliton in this scheme, and right chiral in the anti-clockwise direction. So, for example, if we pick these two guys, BB and BA, and join together like this way, we will end up with this kind of structure, which is the left chiral soliton. These soliton are coming in 3 flavors, as I said, to carry the charge information in the left chiral, right chiral, and anti-chiral ways. So, but we need, at this point, I need some very deterministic way, some very systematic way to calculate all these solitons. So here I'm introducing the idea of the phonon modes. It's not a single charge density wave transition because only one of the band has properly triple band piles instability has been proposed to facilitate the interband transition and the Fermi charge nesting condition. But the point is that when the blue band shifts out, it leaves a vast ground for the remaining 2 indium metallic surface bands to carry the band, to create the band gap, and also the most important thing for my case is that there is a band inversion, which is a clear indication of the topological stuff coming in this picture. I'm not going to talk about this is a first order phase transition, but you can see it's a quasi first order phase transition as the gap opening is a little bit shifted at the high symmetry line. So with these 3 shear mode, 1 shear mode and 2 rotary modes, this can be acted as a basis set for my soliton generator, which I will make all different kind of solitons, and then I will study, for example, their dispersion relations and stuff like that. So this is the scheme how it will work. The 4-fold degenerate ground state, chirality is coming, topology is coming also to this structure, and we can have a soliton and only any of these genes, for example, in 1, 1, 1, minus 1 fashion. So exciting any 2 mode. That's the scheme, that's the chirality of the structure, but the point is, since we have 3 modes, it will generate 4 states, the chiral states, but the 4 other states will also create it, that are the topologically forbidden states. There are some ways to make these states stabilize, but that's the other part of the story. Keep in mind that these 4 ground states we can make for the systematic determination of the soliton generator, and it will work like this way. So we have 4 forbidden state and 4 allowed state, and all that will going to make such a structure. But before going to that, let me show you a little bit of test calculation for that kind of soliton. For example, in the classical theory of soliton, it is understood that defect cannot be mobile. In-plane defects are static in general. For example, here is a in-plane defect and a left chiral soliton is coming through. So it's obvious that this left chiral soliton will be trapped inside this defect. But let's suppose there are other soliton coming, which is anti-chiral soliton. So the defect will be moved like this way by some lattice constant that way. So how it works? These are the results. You can see that we need a chiral soliton anti-chiral soliton to move the defect, because anti-chiral soliton only involve the rotary modes, and the defect can share, move. It seems like the defect is moving. It shares it exchanges the lattice sides with respect to surface symmetry. On the other hand, when we have a proper chiral soliton, it seems like it's pinning those. It is pinning the rotary mode because it involves the shear mode of the system. So that's a kind of test calculation. But all I had shown that to validate these models, for example, the first calculation I had done with my soliton generator was like this way. So here I had additional addatum to trap this right chiral soliton, and I get a very nice matching of Professor Young's science paper. Here we are very lucky to have this W kind of shape feature, and we will essentially perform some other calculations later on. But then the part of that, we are quite close to get this kind of feature where we can have the trapped soliton in the neighboring wire. So that's all for my side for the time being. So the progress is like this way. So charge density wave is supposed in cause one-dimensional topological soliton. There are for degeneracy, associated current state are topological solitons. And I want to build all those minimum 12 solitonic configurations. And later on, chirality and MD, their interaction, intra-wire, inter-wire interactions, and full phonon band structure is coming. So thank you.